Have you ever looked at a massive bridge or a skyscraper that seems to touch the clouds, or even just the fork in your kitchen drawer and thought, how is this thing so strong? Well, today we are pulling back the curtain on the hidden science packed into our most common metal objects. We're going to explore the constant epic battle between human ingenuity and nature's stubborn mission to tear everything back down.
It's a great question, right? I mean, we build our entire world out of things like steel and iron, materials that are practically a synonym for strength. And yet, we all know that given enough time, they weaken, they crumble, they fail. So what's the deal? Let's get into the nitty-gritty of how our toughest materials are secretly trying to self-destruct. And that really brings us to iron's big secret. Its fatal flaw. For all its might, iron has this built-in weakness, a natural tendency to just fall apart and return to a weaker state. And look, this is not some small issue. It's estimated that corrosion, this process, costs the global economy over $2.5 trillion every single year. That's a constant, mind-bogglingly expensive war happening all around us, all the time.
That process is called corrosion. And at its core, it's just the gradual destruction of metal as it reacts with the world around it. You see, what's really going on is that the metal is desperately trying to get back to its most stable, natural form. You know, the ore we dug out of the ground in the first place. It's this deep chemical drive to return to the Earth, and in the process, all our carefully engineered materials just get weaker and weaker.
Now, when you think of corrosion, the most famous villain in this story has got to be rust, right? That flaky, reddish-brown stuff that's the mortal enemy of everything from your garden shovel to giant ships. Okay, let's really dive into this. What exactly is rust from a scientific point of view?
So, while corrosion is the broad, general term for this breakdown, rusting is the very specific name we give to the corrosion of iron and its family of alloys, like steel. It's a super particular chemical reaction, and it turns out the recipe for it is surprisingly simple.
And here it is, the simple recipe for total destruction. You just need three things: iron, oxygen from the air, and water. When you get those three together, you get this new chemical called hydrated iron 3 oxide, which is just a fancy science name for rust. Now, the crucial part here, the real key, is that you need both oxygen and water. If you take away just one of them, the whole reaction grinds to a halt. It's why a nail in a jar of boiled water with no oxygen won't rust, and a nail in the bone-dry desert won't rust either. You need both.
So if the very air we breathe and the water all over our planet are in a constant conspiracy to destroy our most useful metal, how in the world did we manage to build, well, everything? The first line of attack was to re-engineer the metal itself from the inside out, making it fundamentally stronger before it ever has to face the outside world.
And we do that by creating things called alloys. Now, an alloy isn't some brand new element. It's much more like a recipe. You take a main metal, and then you start mixing in other elements, almost like a chef, to deliberately boost its properties. You end up with a new material that is just so much better than its individual parts.
And the results of this mixing can be absolutely wild. Just look at brass, for example. So on this chart, copper has a tensile strength of about 3. Zinc is actually weaker, at about a 2. But when you mix them together to make the alloy we call brass, its strength shoots all the way up to 5. You've literally taken two weaker metals, combined them, and made something way, way stronger. So how on earth is that possible at the atomic level?
Well, okay, in a pure metal, like iron, all the atoms are the exact same size. And they're arranged in this perfect repeating grid, like a crystal lattice. The easiest way to picture this is to think of a box stacked perfectly with marbles. Because all those layers are so neat and tidy, they can just slide right over each other without much fuss. That's actually what makes a lot of pure metals pretty soft and easy to bend.
But when you make an alloy, what you're really doing is introducing atoms of a different size into that perfect grid. So imagine throwing a handful of different sized gumballs into that box of marbles. All of a sudden, those neat orderly layers are completely messed up. They can't slide past each other anymore, they jam up, they get stuck, and that right there is the genius behind alloys. That simple disruption at the atomic level is exactly what gives them their incredible strength. And nowhere is this idea of alloying more important than with steel. See, steel isn't just one thing. It's a whole family of iron-based alloys. And by adding just tiny amounts of different elements, we can cook up this huge range of super steels, where each one is perfectly customized for a specific job. It is incredible how just changing the recipe gives steel completely different superpowers. You add a little bit of carbon and you get mild steel, which is nice and malleable, easy to shape. Mix in some tungsten and boom, you get super hard tool steel that can handle crazy high temperatures. And probably the most famous one, you add chromium and you create stainless steel, which is not only hard but, and this is the big one, is super resistant to rusting.
And this is exactly where all that science pops up in your day-to-day life. That flexibility of mild steel, that's what makes it perfect for car body panels that have to be pressed into all those curves. That toughness and heat resistance of tool steel, that's why a drill bit can spin like crazy and not melt from the friction. And the whole reason your dishwasher or your washing machine can spend their entire lives being wet without turning into a pile of rust? You guessed it, stainless steel. Every job has its own perfect engineered material.
But here's the thing. Even our amazing, engineered super steels aren't always 100% invincible. So we need another layer of defense. If we can't always solve the problem from the inside, we've got to fight it from the outside. So, how do we stop corrosion in its tracks?
Well, there are two main strategies. The first one is pretty simple. You just create a physical barrier. Hey, if rust needs oxygen and water to get started, then just don't let them touch the metal. Easy enough. The second strategy, though, is way more clever. It's called sacrificial protection, and it's basically like using a chemical decoy. You see physical barriers everywhere. The paint on a car or a bridge, that's its armor. The oil you put on your bike chain, yeah, it helps it run smooth, but it's also physically pushing water away from the metal. Even fancy silverware is often electroplated, covered in a super thin layer of a less reactive metal like silver, to protect the steel underneath and, make it look shiny.
But sacrificial protection, this is where the chemistry gets really cool. The whole idea is you attach a more reactive metal to the iron. And because this other metal is, chemically speaking, more eager to corrode, it basically jumps in front and takes the hit. It will oxidize or rust instead of the iron, sacrificing itself to save the more important structure. It's brilliant.
And this simple experiment shows it perfectly. Look, if you wrap an iron nail in a strip of magnesium, which is more reactive, the magnesium gets eaten away, but the nail stays totally fine. But, and you have to get this, if you wrap that same iron nail in copper, which is less reactive than iron, you actually make things worse. The iron now becomes the sacrificial metal for the copper, and it rusts even faster than it would have by itself. It's all about who's higher on the chemical food chain.
So, from the atomic structure of alloys all the way to the clever chemistry of sacrificial metals, we are in this constant race to outsmart nature's desire to break things down. And it really makes you wonder, if this much incredible science has gone into making a drill bit or a dishwasher, what other amazing stories of human ingenuity are hiding in plain sight in the everyday objects all around you?